let's look at a sample problem. Okay, so let's say I have 25 grams of carbon dioxide gas. Okay, 25 grams of gas, and I put that carbon dioxide gas in a container at STP. First question, how many moles? Whenever I do not have moles, the first thing I need to find is how many moles. Because remember in that mole map from an earlier video, all roads go through mole. Mole is Grand Central Station. It's the connecting thing. It's the one ring that binds them. It connects grams, volume, and number of particles. Okay, so it's the unifying thing. So if I don't already know what fraction of a mole or how many moles of something I have, that's where I have to go first. So how would I set this up? 25 grams of CO2. Take your time to write all your labels. You got to do it. It's important. Now, I'm always multiplying, but multiplying by what? A conversion factor. So I'm either multiplying by a number or I'm really dividing by a number because it's 1 over that value. So if I have grams, notice I start by putting a multiplication sign. I create a fraction. The labels never lie. Just like with unit conversions, labels never lie. I want grams to cancel. And I need to find moles. So what you're looking for is always on top. And if it's a multiple step problem, which we'll look at one of those later on, you might not, the first step might not be what you're looking for, but it gets you closer. So you have to think. That's why labels are really important and they never lie. So I have 1 mole of CO2. Now, carbon dioxide. Carbon, if you go look it up on your periodic chart, has a mass of 12 grams in 1 mole. It's 12 AMUs for carbon atoms. It's 12.0 grams for 1 mole. And oxygen, each oxygen, 15.995. It's rounded up to 16. We have 1 carbon, 2 oxygens. So 12 plus 16 plus 16 again gives us 44 grams in 1 mole. 44 grams in a mole, 1 mole, 44 grams. So I've got it set up. If I set it up, the math will take care of itself because you got a calculator. Numbers on the top, multiply by what's on the top of a fraction. Numbers here, divide by what's on the bottom of the fraction. So, turn my calculator on. 25 divided by 44 gives me 0.57. It's 5688. Yeah, well, excuse me, 5.5681. We'll call it 0.57 mole CO2. So there's my answer. How many moles is this much carbon dioxide gas? A little over half a mole. Once I have moles, I can figure out particles, I can figure out volume because mole is the connecting thing. So how many particles? Well, I could start with my answer. Again, I need a conversion factor, a conversion fraction. I have moles. I don't want to find moles. I already have them. So the mole is what I want to cancel. And notice I'm always dealing with 1 mole here. I'm always dealing with 1 mole here. When we look at chemical equations, then we're going to have coefficients. But for right now, whenever I'm converting from a quantity to moles or from moles to the quantity, grams or volume of gas or particles, it's always how many in 1 mole. So the definition of a mole is 6.02 times 10 to the 23rd. And And CO2 is a molecule. Let me make my running a little neat there. So I have to do this. So I have my answers from before. I'm just going to let all the numbers roll. So it's on top, so now I'm multiplying. Remember, when I'm moving from moles, moles multiply to get to mole. I divide, it's on the bottom of the fraction. So I have moles. I'm going to multiply by Avogadro's number. So to put that, multiply my answer by 6.02. Now, depending on your calculator, you might have an EXP button, or you might have an EE button. This is a second function on this one, so I'm going to hit second, and the blue letters that say EE, and it gives me an E. That E takes care of the times and the 10. It's already in there now. So my calculator knows I'm talking about a really large number. I'm not doing 6.02 and then multiplying that by 10 raised to an exponent. If I put it in wrong, I'll get an exponent value on the 10 that's not correct. So I get 3.4 times 10 to the 23rd. 3.42 times 10 to the 23rd molecules CO2. Not moles CO2, molecules CO2. So in 25 grams, there are 3.4 heptillion, or excuse me, 342 heptillion molecules of CO2 gas. Well, what space is that going to take up? Again, all roads lead through mole, so I have to start with mole, because that's the only direct connection, that's the only direct flight to get to any of these. So, starting with the same situation here, the same value, 0.57. So, I'm just going to reverse my math so I have that number back in my calculator. Set up the fraction. Mole, where's it go? On the bottom. Because I already have it, I'm moving away from it. What am I trying to find? Volume, which is liters of CO2. And the value is always the same, 22.4. Make my L look like an L. There we go. So, times 22.4. This gas will take up 12.7 liters when it's at STP, when it's at standard temperature and pressure. Okay, so if I have grams, I can convert to moles. Once I have moles, I could convert to particles, I could convert to volume. If I had particles, I'd do the same step, this first step. I'd be dividing, but I'd be dividing by Avogadro's number to get moles. And from there, I could figure out how heavy it is, mass. I could figure out what volume it takes up if it's a gas at STP. If I had the volume of gas at STP, again, similar first step, I'd get to moles. It's just I'd have 22.4 that I'd be dividing by. So whatever you're starting with a label, if you already have moles, you can multiply to get anything else. If you don't have moles, but you have either grams or particles or volume, then you can convert to moles and then get anywhere else you need to. So these are all the different possible interrelationships that using that mole map we can calculate.